Hello and welcome to this manufacturing process technology part 2 module 18. We were discussing about how the potential at a point in the near vicinity of a positive central charge because of its atmosphere is dependent both on the main charge as well as the surroundings with an effective radius. So, we actually derived this expression that the total potential psi at A could be recorded as plus minus Zi epsilon d times of A, which is actually due to the ion itself, and a contribution from the environment which is minus plus k Zi epsilon divided by d1 plus Ka, where this contribution comes from the surroundings of the principal ion. So, we kind of found out that the effective radius that would be there of the environment would be actually 1 by Ka divided by K. So, this was corresponding to the surface of the central ion of interest. The ion was having a radius of A, as you may recall, and we had computed this expression with help of a charge equivalence, saying that because of the electroneutrality principle, the central ion's charge would be exactly same and opposite in nature to the total charge of the surrounding of the main ion. So, having said that, now let us look at the application of this to creating an array of such charges. Maybe let us say there are negative charges which we want to create an array, and that too on a surface. So, this is a surface of interest, and we find out what are the effective processes which go on when there is a charge buildup of this one ion and its surrounding translated into an embedded array of ions. Okay, so these are all 1, 2, 3, 4, there are several such negative ions embedded onto the platform of the electrode and in vicinity with the solution. Okay, so there is some kind of an electrolyte in vicinity with that, and we would like to compute what happens at this interface of the solid and the liquid. So, immediately when such a distribution happens, for the case of an electrode dipping into a solution of an electrolyte, the total charge on the electrode surface must balance the total solution charge opposite charge, because obviously if there are negative species on the surface, it will attract all the positive ions from the solution, and there is a thin layer of water. This is a water layer, maybe a monolayer of water, which comes in between as a dielectric layer, disabling the positive charge to go and settle on the top of this electrode as long as there is no active potential which is applied on this electrode. So, there is an electrostatic interaction between the electrode charge and the solution charge. Please be aware again that this charge is bound, so it cannot really go into the solution unless there is a species which leaves with an excess electron or a electron deficiency into the solution. So, therefore, it is always a bound charge that we are talking about, which is interacting with free charge, which is like ions in the solution. So, this is the bound side, okay, of the charges. You cannot have an electron directly getting into the solution from the solid, and that is because the electron is heavily bound by the nucleus or the different nuclei of the species which constitute the solid material. So, ions from the solution may approach the electrode surface only so far as their inner solvation shells allow them to be. So, this is that shell that we were talking about, the solvation shell, because of which there is always monolayer of sort of water, a membrane of water which comes between the ion and the negative charge on the electrode, and the surface array of ions is thus cushioned from the electrode surface by a monolayer of solvent. The line drawn through the center of such ions at this distance of closest approach marks a boundary, which is an imaginary boundary, and we commonly know of it as an outer Helmholtz plane or a Helmholtz layer. Okay. So, this is the Helmholtz layer. The size of the ions forming the outer Helmholtz plane are larger than the total number of ions needed to do a complete charge balance, obviously because these are very finely bound electrons which are densely present over the surface, and this layer of negative charge really cannot be balanced because of a size constraint, because every ion in the solution carries a size around it. But you have to mind that this is an ion, okay. So this is having a specified size. So this layer of charge, which is the closest layer of charge that can come to the electrode, is unable to balance the total charge which is on the electrode, okay. So therefore you have the remaining charges which are all held within the with increasing disorder in the outward direction into the solution, and this layer is known as the diffuse part of the double layer. So it's something like you have a densely populated negatively charged surface, sort of a monolayer of solvation by water, and then finitely interspersed charges of opposite type pulled by the electrode, and then whatever remaining charge distribution or whatever remaining unbalanced charges are left over, there are several such layers which get formulated into the solution unless the charge balance is complete, okay. So obviously this is the Helmholtz layer, and this whole layer of charge until the balance is complete is called the diffuse layer. So we are more interested in the variation of the potential xi with distance from the electrode surface, and if we were to plot this, you can see somewhat characteristic value of psi varying as a function of x, where x is the protruding distance into the solution. The first layer up to the Helmholtz plane is really only a resistive layer, beyond which there is a square distance square influence, because of which the layer is no longer linear, okay. There is a charge unbalance, and that is how the charge assembles. So this is the solution side, but till and until the first layer of charges gets built up or the Helmholtz plane gets built up, you have almost a resistive drop which happens only because of water, okay. And so let us assume that the diffuse layer extends all the way up to delta, and we can try to calculate this from the presumptions made earlier. If you may remember, we had solved an equation of the type del 2 xi, xi is the potential in the near vicinity of a charge by del x2. In this particular case, only one dimension x needs to be followed, as it is a case of symmetry, and also it is only a plane that we are referring to, so it is not a three-dimensional space. So we would only consider variation of the potential function with respect to the x here. So this can be written down as q square xi. Q square is the equivalent of the capital K that we had done earlier in the case of single charge, okay. And here the 1 by q plus k, if you may remember, we had called this as 1 by Ka divided by k, that is 1 by k plus a, as the effective ion radius, okay. So this came out to be the effective ion radius of the surroundings. So having said that, now in case of the electrode, one by k can be replaced, and this is only an approximation, by the term delta, which is the diffuse layer thickness, okay. So this actually comes from the theory of ion association, and I am not going to go into the details of how this approximation came, but you can just, if any of you are interested, interact on the chat portal further for you to be enabled to learn a little more about this. So this 1 by k can be approximated as the diffuse layer thickness delta in this particular case, and obviously, as you may recall, this 4 pi rho by d, the minus sign, is represented as q square xi in this particular case. So, we have general solutions of this equation del 2 xi by del x 2 equal to q square xi as xi x equals a e to the power of minus qx plus b e to the power of qx, and at a distance x equal to infinity, the xi of x equal to 0. You can see here that corresponding to the infinite distance, the potential kind of asymptotically goes all the way to 0 as one boundary, from which we will be able to sort of predict maybe a few facts about this equation. So, obviously, this is possible only when b is 0, the same manner, and xi x in this case, the potential function is actually given by a e to the power of minus qx. Okay. And we already know from here that the rho can be represented as minus q square d xi by 4 pi. In other words, the rho in this case, the charge density, can be minus q square d by 4 pi times of this value right here, a e to the power of minus qx. Okay. So, in a similar manner, we would like to try and see if we can calculate the value of a in this particular case, and try to predict what is the potential function which is available at the almost Helmholtz layer surface, and what is it as a function as it proceeds from the Helmholtz layer all the way up to the end of diffuse layer. See, this is a very important perspective, because ultimately all the electrolysis that is going to happen is across this surface. Okay. And this interface is a very critical issue whenever we are talking about a solution in contact with a solid, and on the solid side we have embedded electrons, and on the liquid side you have ions. So, that is the only way to sort of explain what is going on as interaction between the ions and the electrons available. So, here let charge density on the surface of the electrode be recorded as sigma per unit area. So, obviously, the sigma value becomes equal to minus a to infinity rho dx. Okay. Or in other words, this is what the surface charge density would be given the volume charge density. Okay, because we are only considering the difference in the x direction, or the difference of the potential only towards the x direction. So, if I were to compute this integral, I should be able to from the surface charge density or some of the parameters, able to kind of find out what is the value of A. Okay. So, let us actually do that here. So, the surface charge density is equal in magnitude to the volume charge density over the whole length along the x direction. In other words, sigma becomes equal to a dq square by 4 pi times of a to infinity e to the power of minus qx dx. I have substituted the value of rho here to calculate this expression, and this comes out to be equal to a dq divided by 4 pi e to the power of minus qa, because obviously one of the limits is x equal to infinity. So, this is how surface charge density is related, and in other words, I can always say that the value of A, which is the unknown constant in the differential equation, comes out to be 4 pi sigma e to the power of qa divided by dq. And in other words, if I were to substitute this back into the expression rho x, which is actually a e to the power of minus qx, would have 4 pi sigma by dq e to the power of qa minus or times of e to the power of minus qx. In other words, 4 pi sigma by dq e to the power of qa minus x. So, if we just look back into what really the formulation was, we have a solid side with a densely embedded negative charge on the surface. We have a solvation layer which is in between, and then there is a Helmholtz layer which gets formulated. So if we assume this solvation layer to be very small in comparison to the the ionic radius, and at the surface of this Helmholtz layer you have exactly x equal to a, okay, this value is considered to be negligible, the solvation shell, any event it is only a one layer of water. So we get this value here as 4 pi sigma dq at psi at a times e to the power of 1. So this actually is the potential available whenever a solution comes in contact with a surface, and we call this potential normally the zeta potential. So this is a very important term as regards electrochemistry, because it is the zeta potential which is going to be able to actually define some of the things that we do in electrochemistry. So there are again, if we really looked at effectively two components which make up the total potential drop across the interface. Obviously there is a potential drop which is in this particular Helmholtz layer, and then there is a drop which is there in the diffuse layer. So if we looked at this model as a capacitance model, we would definitely have the total capacitance of the double layer C made up of that due to the inner layer, and which we designate as, let us say, the Helmholtz layer CH, and that due to the diffuse layer which we may designate again as CD. So we can have this total capacitance here all the way up to, let us say, the diffuse layer here as a combination, a series combination of CH and CD. Okay, so we can have 1 by C equals 1 by CH plus 1 by CD, so that the total net capacitance comes out to be CH CD by CH plus CD. And there are two different cases. If supposing the CD value is much less in comparison to CH, then the effective capacitance, let us say this is C effective, becomes equal to CD. Okay, and if CD is very high in comparison to CH, the effective capacitance becomes equal to CH. So this is called the Helmholtz model, where we consider Helmholtz capacitance to be negligible, and this actually is known as the Guy-Chapman model. And these are important for the perspective of doing electrochemistry at a surface whenever we want to take care of the measurements. However, we are more interested in the zeta potential and the way that the electrochemistry may happen on an ECM process. Okay, and for that, now let us actually go back into the very fundamental basics about how mass transport occurs and what is the electron exchange process considering a ECM operation. So in considering such a electron exchange reaction at electrodes, we are concerned essentially with a layer of solution very close to the electrode surface. There should, however, be some means available for oxidant or the reductant to reach the electrode surface, and there are a number of ways which this can occur under general heading of mass transfer processes, and they are migration, it's a movement of cations or anions through a solution under the influence of an external potential between the electrodes placed in that solution. Diffusion, it's basically concentration gradient driven flow. The electrode reaction depletes the concentration of the oxidant or reductant at the electrode surface and produces a concentration gradient there. So this gives rise to the movement of species from the higher to the lower concentration. It occurs in both charged and uncharged species. And then we have convection, which is because of again the thermal or the stirring effects which can arise extraneously through vibration, shock, setting up of temperature gradients within the electrolyte. So these are the three main mass transport mechanisms which would influence the travelling of the ion across the solvation shell, so that there is a deposition on the electrode of one kind, and similarly a taking out of the solid from the electrode of at the other electrode or the other polarity. So generally in the ECM electrochemistry, when a metallic body is submerged in an electrolyte, the metallic atoms leave the body and become ions, and the ions move to the body and become atoms. Okay. So the process goes on continuously and an equilibrium is maintained, and a potential difference exists between a point on the surface of the metallic body and an adjacent point on the electrolyte, and this potential difference is known as the electrode potential, which is also the zeta potential, and the electrode potential varies depending on the electrode electrolyte combination, and if two different electrodes A and B are immersed, a potential difference between these two electrodes will exist, since the potentials of A and B are different with respect to the electrolyte, which may result in some kind of a current or a voltage difference between both the electrodes A and B. So this is the general electrochemistry process, and how the ECM can be obtained from this electrochemistry process is in the following manner. So let us say the reaction at an anode is basically related to steel. So we are having the iron to ferrous ions conversion process, meaning thereby whatever iron is there on the surface leaves as Fe plus 2 ions on the solution and leaves 2 electrons with the electrode concerned. Okay. Now if supposing we had a brine solution or just a normal kitchen salt water combination, the electrode metal Fe would dissolve, okay, and the 2 electrons that have been left because of that would actually further try to break down water into H2, which is a gas form, and it kind of bubbles out, and hydroxyl ions 2OH minus. Okay. Now you can think of it that there is Fe2 plus present in the solution because of the removal from the iron electrode, and then there is this 2 electrons which are depleting the hydrogen the water into the hydrogen gas and hydroxide ion. So obviously there would be a reaction between this OH and the Fe plus 2 because of its availability in abundance within the medium, and as a result you can have ferrous hydroxide FeOH2 formulated in the medium, which is actually a precipitate. Okay. So it is an insoluble form of compound of iron, and it precipitates, and it actually is there at the bottom of the electrochemical beaker or the jar where this whole reaction is taking place. Now, so this is something very interesting happening, that on one hand you are able to do the reverse of electroplating by taking out iron from one of the electrodes, converting it into the ionic state, and then using the same electrons that iron had given earlier to convert this Fe plus 2 into FeOH2 ferrous hydroxide, which is actually insoluble. Okay. So it does not redeposit on the other electrode through which the electron has been pumped in, and at the same time it goes and falls at the bottom. Okay. So whatever is coming out is not getting deposited in the other electrode. In other words, it is going to be subtractive process, or machining is happening at the behest of this reaction. So with this kind of electrode metal electrolyte combination, the anode dissolves and hydrogen generates at the cathode, leaving the cathode shape unchanged, and this is the most important characteristics of ECM process, that when we are doing a die sinking process with ECM, I had mentioned it earlier, the shape of the cathode, which is actually the tool in our case and is also an electron emitter, does not change. So whatever is the die or whatever is the overall shape of the cathode remains as such, and it is useful embedding onto the surface which is being machined. So it should be noted that for ECM, the choice of electrodes and the electrolyte must be such that no deposition at either electrodes can take place of whatever is coming off, and that is how electrochemical machining is sort of performed. So let us now look at the a little bit of how you calculate the material removal rate, and I think I had earlier illustrated the Faraday's law, through which we had the mass that is taken off or transported in a electrochemical system is dependent on the current time product and is also related to the gram equivalent weight of the species. So, borrowing this theory, we can probably try to see what is the m dot. Okay, so that's the material removal rate, the rate of mass removal, and we can call this by putting a very interesting term here, which is this Faraday constant, and we assume this movement of material as moles. Okay, and you know that 1 mole is 6.023 into 10 to the power of 23 atoms or species or ions or whatever it gets dissolved. So, basically we are considering only the molar mass and all things related to a mole or number of moles being transferred, which makes it easy because as you know that the weight of 1 mole of a species is exactly equal to its atomic weight. Okay. So, that is how in chemistry, in basic fundamental chemistry, things have been categorized. So, here also a similar manner, the m dot or the rate of removal of the mass obviously depends on the I, the current, which is the rate at which charge is transported. So, basically do not have the current time product anymore, but the m dot enables this current time product to change only into current times of the gram equivalent weight, which is again function of the atomic weight, that is the movement of or that is the mass of 1 mole atom of a particular species divided by the valency which is needed. Obviously, if you are removing Fe plus 2, you have to have 2 electron transfer. So, number of charges that would be needed for removing Fe plus 2 would be exactly 2 times or 2 moles for 1 mole of Fe plus 2. So, that ratio needs to be maintained here, which is actually given by this A by Z or equivalent weight, and this is also related to sort of this I is still charge and we need to somehow change into from the rate of transport of charge into rate of transport of moles of charge. So, we divide this by the charge of 1 mole electrons, and 1 mole of electrons would have 6.023 10 to the power of 23 times of 1.6 10 to the power of minus 19, which is the charge on 1 electron coulomb, and this figure comes out to be 96,500 coulomb approximately. Okay, so, that is how Faraday constant F is derived. So, if I were to multiply this or divide this I, which is the dq by dt or the rate of change of or rate of transfer of charge into the solution of into the electrochemical setup by this term F, it would typically mean what is the rate at or what is the rate of molar change of charge within the species. So, and it would be very good way because in 1 mole you know that A by Z mass is removed. Okay. So, the m dot therefore which is also the material removal rate in grams per second, okay, is given by AI by ZF. If I were to convert this into the volume rate of removal of material, I would have to divide this by density rho, and so effectively the material removal rate in centimeter cube per second comes out to be, and this is the volumetric material removal rate, comes out to be AI by rho ZF centimeter cube per second. A is the atomic weight, gram atomic weight of the metallic species, the I is the current in amperes, rho is the density of the anode in gram per centimeter cube, and Z obviously is the valency of the cation, and I have already explained to you how this F factor or the Faraday constant is emerged. So, this is a sort of ballpark understanding of how the volumetric material removal rate can be created. However, this is only a single phase system, but in actual real scale operations you do phased alloys, and therefore each of the alloys or each of the elements participating in those alloys are having a different characteristic density, different characteristic weight. So, we will try to assemble or envision a model where all these alloyed systems are present, and how do we do the rate calculation in that case would be the next step that we will like to do. But I have to close this module in the interest of time. So, as of now, goodbye from here. Next module we are going to do alloyed systems. Thank you.